Chapter 17 is all about the chemical and physical properties of water. And to understand those properties, we have to understand how a water molecule is built. Okay, so this is a bead and spring model. The red bead is my oxygen. The white beads are my hydrogens that are covalently bonded to that oxygen to make that triangular structure. Okay, what that does, let me draw it here. Here's my oxygen. Here's one hydrogen covalently bonded to it. Here's another hydrogen covalently bonded to it. And remember, oxygen has 6 valent electrons. Okay, so there's one being tied up with this bond. There's one being tied up with this bond. That gives me 2 more. It gives me 2 pairs of non-bonding electrons orbiting that oxygen. And oxygen is so electronegative. If you remember back on our chapter on electronegativity, we talked about how the elements in the upper left corner, let me grab my periodic table here. Left as you're facing it. The elements in the upper left corner of the periodic table are the most electronegative. Okay, meaning they can steal electrons from other atoms easily, and they have a great affinity for doing that. Fluorine is the most electronegative element on the periodic chart. Oxygen being right next to it means that oxygen is very electronegative. And what that means is oxygen is very good at stealing an electron from another atom. Okay, because it only needs 2 to fill that shell to be like neon. It's very good at grabbing those 2. So when it covalently bonds to hydrogen, even though it's a covalent bond and they're sharing those pairs of electrons, the electrons are spending more time around the oxygen than they are around the hydrogen because of the electronegativity of oxygen. Okay? Now, because of that and because of these extra bonding pairs of electrons on this side of the oxygen, a water molecule is charged. It has polarity. Okay? And polarity is just a separation. If something is polarized, you've separated it. Okay? Like the Earth has a magnetic north and a magnetic south. It has a polarity on its magnetic field, okay, because they're separated. Water molecule has a polarity of charges. So as I approach a water molecule from this side, I feel a negative charge. Okay, it's a partial negative charge. So you see that symbol, which just means partial. And when I approach the water molecule from this side, I feel a partial positive charge because the hydrogens feel like a proton, okay, which has a positive charge, because all a hydrogen atom is a proton and an electron, but that electron is being donated to this bonding pair. They're spending more time around the oxygen. So what I really feel when I approach, what I feel electrically when I approach the water molecule from this side is a positive charge and a negative charge here. That gives water a lot of its unique properties, okay? That polarity helps it dissolve things. It helps it hydrogen bond so it can stay a liquid at a vast range of temperatures. It gives water a lot of its properties. Now let's talk just a minute about hydrogen bonding. Hydrogen bonding occurs when the water molecule, the negative side of one water molecule, is attracted to the positive side of another water molecule. Okay? So I've got the hydrogen on this water molecule that has a slightly positive charge, and I've got the bonding pair of electrons on this water molecule that have a partially negative charge. These guys do here. So there's going to be a bond that forms there. Let me draw it like that. Between the partially positive side of this water molecule and the partially negative side of this water molecule. Likewise, another one can form to another water molecule. Okay, so you get another hydrogen bond forming here to these bonding pairs. Now those hydrogen bonds, those are intermolecular bonds. In other words, they're between 2 molecules. Okay? they're not the same thing as the intramolecular bond that is between this hydrogen and this oxygen. That is a covalent bond here. This is a hydrogen bond. So covalent bonding is intramolecular, it's within the molecule. That would be like the springs on my model here. Those would be covalent bonds. Much harder to break than that hydrogen bond, which is an intermolecular bond between two molecules. Okay? So when water evaporates, when it goes from the liquid to the gas state, let's say I've got two water molecules here. Here's one, here's another, and they're hydrogen bonded together. The negative side on the oxygen is attracted to the positive side of the hydrogen of this water molecule. And there's a bond that forms there, that's a hydrogen bond. Well, if you break that bond, that water molecule becomes a gas and goes up into the atmosphere. We call that evaporation. Okay? So it's a fairly weak bond. It breaks way before the covalent bond would break between this hydrogen and this oxygen inside of this molecule. All right? So these are tightly bound together. This is a much weaker bond. So when you boil water, so I've got liquid water and it's boiling, it hits 100 degrees Celsius, and you start to get steam off of the top of your pot that you're boiling the water in. The steam is a water molecule. You've broken the hydrogen bonds at the surface of the water, and they're going up into the atmosphere, okay, into the room. You're not breaking the covalent bond. You're not making hydrogen and oxygen gas in the room. You're just making water vapor because you're breaking that hydrogen bonding. The hydrogen bonding is very important for water, for life on Earth, because what it does is it keeps water in the liquid state from 0 to 100 degrees Celsius. That's how the Celsius scale is adapted to the physical properties of water. So 0 Celsius is where water freezes and forms a lattice shape. 100 degrees Celsius is where water goes from a liquid to a gas. Okay? That's a wide range of temperatures we experience around the Earth where water can remain in the liquid state. If it were not so, life as we know it on this planet wouldn't exist. So hydrogen bonding adds to that. Okay? Also, it adds to other properties, like water has a high surface tension. And surface tension is an inward force. Those water molecules are all attracted to each other. And if you put water in an environment where it's not attracted to its external environment, okay, it's going to pull in on itself and beat up. Let me show you what I'm talking about. So I've got a piece of wax paper here, and I'm going to put a drop of water on it. Now wax is very nonpolar. Okay, it's hydrocarbons. Any way you approach those molecules, there's no charge. Okay, it's very neutral. Water is very charged because it has polarity. It has that partial positive and partial negative side. So when you take something very polar like water and you put it on something very nonpolar like wax, it beads up. Okay, see how my water is beating up and running down the wax there? It doesn't want to touch the wax, if you can look at it like that. So it makes a sphere. A sphere is the shape where it has the least amount of surface area touching the wax. That's why water beads up on a waxed car. Okay, that's that surface tension. Another way to illustrate that is if I took a penny and I started putting drops of water on it, I can get a lot of water on that penny before it spills over the sides. See how much water I've got on there? Because of that surface tension, that hydrogen bonding, where the water is attracted to itself, it's going to hold onto that penny. You can put 100 drops or more onto a penny of water before it spills over because of surface tension. Okay? That's due to that hydrogen bonding. Okay, so a lot of water's properties are due to hydrogen bonding. Some of them though, are due to the lattice formation that it forms when water goes from a liquid to a solid. Okay? When water is a liquid, it's hydrogen bonded together, but it's kind of, it's not as structured. The formation of all the water molecules are kind of spread out. Okay, so it's more dense than when it freezes. When water freezes, it takes a very rigid structure. spreads out, becomes less dense, and that's why ice floats. Okay, if I take some water, and I've got an ice cube here. So this is liquid water, and this is frozen water, and I put the ice in the water, you see it floats to the surface. Okay, because solid water is less dense than liquid water. That's unique. Okay, most substances in their solid form are more dense and would sink. But water is a little different that way. And because of that, our poles, North and South Pole, the ice there has water underneath it. Okay, the ice floats. To illustrate that further, I've also got a beaker of isopropyl alcohol here. Now the density of liquid water is right around 1. The density of isopropyl alcohol is a lot less, around 0.8 or so. Okay, if I take ice and put it in alcohol, okay, this is just isopropyl alcohol, it sinks. See the ice sinking to the bottom there? Whereas when I put it in the water, it floated. Because the density of ice is somewhere between the density of liquid water and isopropyl alcohol. Okay, it's less dense than the liquid water, so it floats. It's more dense than the isopropyl alcohol, so it sinks. And that's a good illustration to show you how the density of water, of H2O, changes as it changes states. Okay. Liquid to frozen. Okay, now, because of the polarity of water, because it has a partial positive and a partial negative side, it's a very good solvent. And a solvent, the definition of a solvent would be a dissolving medium, a solution that dissolves other substances. Okay, that's the solvent. So water is considered to be the universal solvent because so many things will dissolve in it, especially salts. Here's why. Let me erase my hydrogen bonding here. Okay, here's my water molecule. Now, if I put salt, sodium chloride, into water, the sodium ion that was ionically bonded to the chlorine anion in that salt, the sodium ion is going to be attracted to the negative side, that partial negative side of the water molecule. The chlorine anion, which has a negative charge, is going to be attracted to that partial positive side of the water molecule. So it's essentially going to tear the salt apart. So my solid sodium chloride crystal is going to dissolve when I put it in water because it's going to be attracted to different, the cation is going to be attracted to one side of the water molecule, the anion is going to be attracted to the other. Okay, and that's why water is considered to be the universal solvent. So many things will dissolve in it, especially if they're ionically bonded together. When you take something that's ionically bonded together, like a salt, different types of salts, and you dissolve them in water, you make what we call electrolytes. Okay, electrolytes are just charged ions in solution. And they're very important, especially in the body for like, oh gosh, calcium ion, magnesium ion are involved in all sorts of things in the body. Muscle contractions, nerve impulses, things like this wouldn't occur. That's why we need water in our body to dissolve those salts and those minerals that we take in to make them electrolytes so that they can do their function inside our body. Okay? Now, I got another way to illustrate this. It turns out water is not that great of a conductor of electricity. And remember, electricity is a flow of electrons, okay, through a solution. So if I've just got pure water, electricity will flow through it. Electrons will be passed from water molecule to water molecule, but not as efficiently as if I add ions to it. Okay, if I put salt in water, it will conduct electricity a lot better because it's easier when you have these charged ions dissolved in that water to pass electrons from one molecule to another and conduct an electrical current. Okay, let me show you what I mean. Okay, this bottom graph here is conductivity. it's a measure of electrical current. And I've got a probe here. If you can see it, let me stretch it out as far as I can. Here, I've got a few probes. This probe has a little metal on the end, a little metal probe on the end of it that measures electrical current through a solution. So I'm just going to put it in this pure water, and I'm going to press collect. And you'll see the graph start to fill in here at about, I don't know, 550 microsiemens per centimeter. So it's a very low current there of electricity is traveling through that probe. But what if I take some salt, and put it in the water? Okay, watch my graph as I add sodium and chloride to the water. The water molecule pulls them apart, so the sodium ion is attracted to the positive, or the negative side of the water molecule, the chlorine ion to the positive side. Now see how that conductivity increased? All I did was add salt to water, but I formed ions. I formed sodium ion, cation, and chlorine anion, and they're very more efficient at passing electrical current through the solution than just pure water is. That's why you see that conductivity graph spike so much right here. Here's where I added, this is before I added the salt. Okay, it was flatlining at about 550 microsiemens. Then I added the salt. Now it's up 21,000, over 21,000 microsiemens per centimeter, okay, because of those ions in solution. So that's a good illustration of how good of a solvent water is. Okay, now the salt that I put in there would be the solute, S-O-U-L-T. Okay, the solute is the salt, the water is the solvent. And together they make a solution. So I made a solution of salt water by adding the salt, the solute, to the solvent, the water, and made a solution, and it conducts electricity very well because of those ions. Okay? So that's a good illustration of the polarity of water. I've got another one I want to show you. This one is an illustration of hydrogen bonding. So let me change probes again here. Now to illustrate how effective hydrogen bonding is for water, especially to keep it in the liquid state, I'm going to do a little demonstration here where I've got two temperature probes, okay, and on one of the probes I've got filter paper wrapped around both, but on one probe I'm going to put acetone, okay, and acetone's chemical structure looks like this. That's an acetone molecule, and it weighs 58 atomic mass units. Now remember, water, it's shaped like this, and it weighs 18 atomic mass units. So water's a lot lighter, okay, than acetone. And water should evaporate. It should go from the liquid to the gas state a lot easier, a lot quicker than acetone should, because acetone weighs so much more. All right, but let's see how it really happens here. So I've got some acetone in a little squirt bottle, and I've got some water in a little squirt bottle. And what I'm going to do is I'm going to wet that filter paper down from one of the probes with acetone so that it's saturated with it. And the other one with water, so that it's saturated with the water. Okay, and then I'm going to hit collect. There we go. All right. Now the red line here, erase this so you can see it. Temperature 1, the red line, that's my acetone. blue line is my water. Now remember, acetone weighed 58 atomic mass units. Water weighs 18 atomic mass units. So you would think the water would evaporate much more easily, much more readily than the acetone. But as you can see by the temperature change, and remember, as something evaporates, it cools. It has a cooling effect. So the faster it's evaporating, the more drastic of a temperature change you're going to see. All right? So what we're seeing here, the acetone is evaporating very rapidly. And you can test this yourself if you got some fingernail polish remover, put a drop on your desk, watch it, it'll evaporate very quickly. Water, a lot slower. Okay, the water is evaporating, it's coming down, it's cooling off. That's why when you run, you start sweating, it evaporates the water out of your body. It has a cooling effect to cool you down until your body maintains homeostasis, stays around 37 degrees Celsius by either closing your pores and causing you to shiver, to warm up, causing your muscles to shiver, or if you're hot, opening your pores and allowing you to sweat, because as that water evaporates, as it goes from the liquid to the gas state, those hydrogen bonds break, okay, that cools you down. And you can see that cooling effect here of water. But look at acetone, okay? So even though it weighs 58 atomic mass units, it's evaporating very quickly compared to the water. Okay? Why is that? If water weighs a lot less, one water molecule weighs 18 atomic mass units, and acetone weighs 58. Why is the acetone going from the liquid, because I started out as liquid acetone, just in a little bottle here, and I put it on my filter paper, to the gas phase, so the acetone went from liquid to gas, so much easier than the water? Well, the answer is hydrogen bonding. Okay? The acetone molecules don't hydrogen bond together, so they'll just go off into vapor a lot more easily. They're not attracted to each other. They don't have that surface tension. Okay? Like the water does. The water, because of its hydrogen bonding, one water molecule being attracted to another water molecule, to another, for one of them to break free from the surface of that filter paper and go off into the gas state, you have to break that hydrogen bond, and that's harder to do. Okay, so I have to break this bond, that intermolecular bond, to let the water go. So even though water weighs less than acetone, it only weighs 18 atomic mass units, it's still hydrogen bonded to all the liquid below it. So at the surface, those water molecules that are evaporating off first, they're doing it very slowly because of hydrogen bonding. Whereas acetone, very quickly, because there is no hydrogen bonding there. Okay, remember that structure of acetone? It was because of the shape of it, the structure of it, you don't have that charge, you don't have that polarity, you don't have that hydrogen bonding. So one acetone molecule isn't hydrogen bonded to the others. So it'll leave at the surface, where the surface of the liquid is. The acetone, it will evaporate very quickly, very readily. And that's what that diagram illustrates. Okay, to sum all that up, the properties of water are unique. And life wouldn't exist on this planet if it weren't for those unique properties. Okay? Water has a very low vapor pressure because of that hydrogen bonding. Vapor pressure is the pressure for water to go from a liquid to a vapor. Okay? The tendency for a molecule to leave the liquid state and form a vapor is its vapor pressure. Water has a low vapor pressure because it has a low tendency to evaporate because of hydrogen bonding. Okay? Surface tension, where water molecules are attracted to each other, and if you put them in a non-polar environment like my wax paper, it beads up, the water does, because it pulls in, it's attracted to itself, but it's not attracted to that non-polar wax. And a sphere is the shape that has the least amount of surface area, and that's why it pulls up like that. Polarity, the ability to dissolve substances, water has, because the shape of the water molecule and the separation of charges makes it a universal solvent. All these properties are unique to water. The density, as water goes from the liquid to the solid state, forms that lattice formation, spreads out and becomes less dense so that it floats. okay, on top of liquid water. That's unique to water because most solutions, most substances, when they go from the liquid to the solid state, become more dense. Okay, but water becomes less dense. All of those properties of water make life possible on this planet and are unique to water because of its structure, because of its polarity, because of its hydrogen bonding. And that's really the crux of chapter 17.